back, everybody. Just a quick reminder for all those sitting in the mask zone, masks must be worn. And now it is my privilege to present the next presentation by David Colls on an EV trip planner for Australia. Big round of applause, please.
Hi everyone, yes, I'm David Colls talking about an EV trip planner for Australia and Aotearoa, New Zealand. It's called Tripler, and we'll learn a bit more about why and what today. So here's a photo of me with more hair at another great community event, the Melbourne-Roubaix bike ride earlier in the year. I also currently have the privilege to head up Data Platform and Products Group at MYOB, whose mission is to help more Australian and New Zealand businesses start, survive and succeed. In my previous role at ThoughtWorks, I also co-authored a book, Effective Machine Learning Teams, with some of my colleagues, and so some of the approaches to building an app with data and AI that I'll discuss today are also covered in EMLT. So our journey today, we'll start with some context around EV adoption, around challenges with trip planning, why it might be an important problem to solve, and then to be able to make more progress, continue on our journey, define the problem more precisely. Then I'll take a long and winding road through the build phases, the challenges that I encountered, how I worked around those. I do hope we'll be making good time nonetheless, so no one will need to ask, are we there yet, until we reach the demo. And from there, I'll share briefly what I learned through the whole process, which was a lot of fun overall, and then think about directions this could go next and for our journeys tomorrow and the next day. Along the way, if you look out to the left and right of the vehicle, you'll see a lot of interesting Python libraries and services that you might want to explore in your own projects or in your professional capacity. So some context. If we think about sustainable transport, it's going to be imperative to address walking, cycling, active modes, public transport to improve the sustainability of our transport system. But battery electric vehicles can also play a large role, given that they represent an 80% greenhouse gas reduction over internal combustion engine or ICE vehicles. And when it comes to EV adoption, there's a challenge. A lot of the driving will be done locally, and the challenge there is to provide charging options for EVs that are accessible close to home for people who may not be able to charge an EV at their home. But it's also very important to solve for road trips, because these are a factor that drive adoption and purchase decisions around vehicles. And these are the most demanding use cases for EVs in Australia at the moment. So this is where I'll focus today in terms of the context. And who doesn't love a good road trip? Here I am many years ago, about as far as it's possible to get from Naarm, Melbourne, on a road trip in Australia, on the land of the Bayungu people, in a vehicle that wasn't an EV, but it did have pop-up headlights, so I think that still counts as pretty cool. And when we think about road trips and EVs, like the term that probably comes to mind for most people is range anxiety. But the reality is that EVs for sale today have an average range of 450 kilometres, and the best top out at over 700 kilometres. Along with apps that can plan the whole trip for you, a road trip in an EV now looks a lot like a road trip in an internal combustion engine. The similar travel time, similar stop times, presuming you want to take some breaks, and not just speed down the highway with no regard for the land you're travelling over. Until you hit an inoperable charger, as I did on my first road trip, and then another inoperable charger. And so your range profile starts to look a little bit different. You have longer stops at slower charges, more wait times, and you're charging at a less efficient point on the EV's battery. So in general, we're not using the infrastructure as efficiently as we could. And this isn't limited to me. The majority of drivers have found an issue with an inoperable charger on EV road trips. So range anxiety doesn't capture the problem very well. In fact, it's charger anxiety. And the conversation earlier this year defined charger anxiety is the question of whether you can find somewhere reliable to recharge when you're away from home. And they've noted that Australia's public chargers are not common enough or reliable enough to give drivers that confidence. I should say this doesn't mean you shouldn't think about EV road trips. All of these places, from Eden to the Alps to Kangaroo Island, are accessible in EVs, with maybe just a little bit more planning. So what is it that we should do about it? The Australian government has advice, as we saw earlier, that some EV planning apps can plan the whole trip for you, but having alternate EV charging options is a smart move. Of course, we're also building out infrastructure in terms of the actual chargers that we need to make road trips more feasible, in the physical sense and in the digital sense as well, where EV Council and others are driving initiatives to report on charger availability and reliability. In this mix, I thought, why not both? Why not build an app as a piece of our digital infrastructure that can provide that resilient trip planning advice to support adoption of EVs? And this, as I said, doesn't just benefit the drivers, but the users of the app, but it benefits all EV drivers in that it enables us to use our existing infrastructure more efficiently. So that all sounds good from a hindsight perspective, but moving forward in time, as I'm constrained to do, I had to think a little bit more about what was the actual problem that I'd encountered on the road trip and how could I frame it in a way that was amenable to a digital solution driven by data and AI. And in that regard, I thought about these apps that can plan the whole trip for you. And my thinking led me to conclude that these are based on a philosophy of optimal plans. There is one best solution for a road trip. And that small changes to the plan would make a small difference to the outcome. So I guess thinking about range anxiety, there are a range of factors that affect the distance an electric vehicle can travel on a charge. They're much more susceptible to headwinds, adverse weather conditions and so on. And so it would be nice to understand whether any of those small changes might make a big difference to the plan. They also assume that the data is accurate, that the status of any charger you might choose to visit at planning time is the status that you will find when you arrive, and also assume that you can execute that plan pretty perfectly. And I might say that in a nod to Lily Ryan's talk tomorrow morning, like these might be some falsehoods we would believe about reality with a perspective of abundance, as most of the trip planners come from more mature markets with more dense charging networks. Instead, I wanted to frame up a planner that was about resilient plans. I wanted resilience. I wanted multiple good enough solutions. If it might take 20 minutes longer over 8 hours of driving, that's much better than having that 8 hours turn into 16 hours. That, as I said, the small changes can make a big difference. If we wanted to understand how decisions on the day might impact where we stopped, then I'd really like to be able to play around with different scenarios and see the impact of small changes in an interactive way. I'd also assume that data is unreliable. I've had both false positives and false negatives when it comes to the status of charges in our digital infrastructure, arriving in reality to find that it doesn't always match up. And of course, that execution would always be variable from roadworks or delays through to major environmental impacts in our Australian landscape, such as floods, or, I mean, we might remember the pictures of traffic tailbacks in the 2020 bushfires, and indeed I had friends in Western Australia whose EV planning was affected by bushfires this summer. So we need to consider all of these factors to make our trip planning more reliable. And this is what I might say, again, if we think about falsehoods about reality, let's take a defensive approach to reality and assume scarcity rather than abundance. So with that in mind, I set myself a task to build an app to solve these problems and deliver a more resilient experience. And I wanted it to be a product, and as we know, products need to be desirable, feasible, and viable. And when it comes to building products with data and AI, that tends to map to the fact that there's a user need, a problem that we can solve. In that case, I treated myself as the main user, which was very convenient for asking, did it solve my needs? But we also need an analytical technique. And so this might be anything from moving averages to deep learning solutions or generative AI, or in this case, operations research techniques. So we need a technique that's been developed and deployed in the field before that makes solving this problem feasible. And then to make it viable or make it economic, we need access to data that we can curate in a way that's economical for this solution, and in a commercial environment, which this isn't, that's also economically competitive into the future as well, and that enables us to solve for enough use cases. So these are like some of the considerations that we tackle from a product perspective in effective machine learning teams as well. And so taking that lens and asking, can we build it? I also wanted to reduce the risk that I would get something useful out of this process. If we're doing this in our professional capacities, the risk might be hundreds of thousands of dollars that's at stake. In this case, it was a few weekends, but I still didn't want to waste my weekends. So I took a phased approach to building. The first was to test that this technique was feasible to use to develop resilient trip plans. And so I called that a proof of concept. We'll dive into each of these stages over the next few slides. This is where the road gets a bit long and winding. The second was to demonstrate the riskiest assumption that it could be built with real-world data. So we could solve trip planning for enough cases, not just the simple one where we've tested the algorithm, but can we get real-world data and solve it for real-world data? The third was the user experience or the user need. Like, could I deliver an interactive experience that I'd imagined, which is also different to existing trip planning apps, which often require a full replan should you change something. With those elements demonstrated, I could then go on to build what I called an MVP. It was initially for just Victorian data, again, keeping it simple, but it was very easy to extend it to Australia data. And now more recently, as I test drove this talk with an MYOB audience that included people from Aotearoa, New Zealand, I wanted to also include New Zealand road trips, even though they don't necessarily suffer from the same problem of scarcity. From that point, there's lots of different directions you could go, incremental improvements, and so there's a few things that I've got bubbling away in the background. So starting with the really simple trip concept, I wanted to boil this down, as is often a good idea with data and AI initiatives, boil it down to the simplest thing that can demonstrate what you're trying to prove, the simplest experiment. So simplest model of a trip I could come up with, we have a destination, and then we have a route to that destination. Again, this is an Australian talk, excuse my pronunciation. We have a route to that destination that has charges on the route or maybe close to the route. We could simplify that into just an array of distances. So we have distance from start point to first charger and every intermediate point along the way. At each of those charges, we also have a value for the power of that charger. So that determines how quickly the vehicle charges and how attractive it is to stop at that charger. And then we have a vehicle that has a range. So this is the simplest trip I could come up with, and this is what I used to test the feasibility of discrete optimization. And this is the AI technique that I chose. Other trip planners use different techniques, but discrete optimization has 4 elements. The first is an objective, and this is what we want to minimize or maximize. And so in this case, the objective I chose was to minimize trip time. With that fixed trip and assumption of fixed speed, there's no variation in travel time, but it's the stop time that varies. So we're trying to minimize the sum of all the stops, which has a variable component and a fixed component. Then the second element is variables, and these are the things that are going to inform our plan. They're going to tell us what to do. And the most important one is how much do we fill and at which charges do we fill the car to reach our destination. To add to that, I also added an arrival charge, which helps us with the third element, which is we add constraints to model reality. And so the reality of driving an electric vehicle is what you put in, you use up as you drive to the next location. And so this is the main constraint that we model. We also can't put more than 100% state of charge into the battery or drain it less than 0%. So these are our reality constraints that reflect what it's like to drive an EV. And then what makes discrete optimization and operations research techniques like really flexible for modeling business problems is that we can add other constraints that reflect the scenario that we're trying to achieve. And so this is where I could actually build in the resilience constraints. We should have backup options as per the federal government advice. I could build in those constraints into the trip plan. So we can require that when we charge at each charger, that we have enough charge to get not just to the next one, but the one after that, or even n charges further down the line. Alternatively, that we can return to a previous charger on the trip. We can also do things like require a minimum state of charge or a destination arrival state of charge. But most important was knowing that if I were to skip any charger, you'd still have options to recharge at the next one on the line. So then putting this all together, using a bunch of Python libraries. Here we're still in the notebooks phase, but using Google's OR tools and matplotlib to visualize. Then we can see some different plans, and these plans are differentiated by the constraints that we put on them. The first one, we just want to arrive with 20% of charge. The other one, we actually want to be able to get to the next +1 charger at every point. So they have different plans and different arrival times. But we can see that this is a feasible technique because if we do actually have a faulty charger, we can simulate that too and validate that the plan is recoverable from that point. If we have the resilience constraints, may not be the case if we don't. These looked a little bit like ripples, I thought, and so that's where the name Tripler came from. So POC is validated. On to the next stage, real-world data. It was actually pretty easy to take a trip, in this case from Melbourne to Forest in the Otways, I think, using a variety of services and find the charges that were close to that route and project them to the nearest point on the charge on the route. And so that used open route service, it used open charge map, and it used Shapely to do the geometry. So now we've actually taken some real-world data and we've compressed it into our simplified representation of the trip. It's looking good so far. We can build that array of distances and charger powers until we start to discover real-world edge cases. And the first of those is illustrated by Shell Colls Express Taylors Lakes, which is a 350 kilowatt charger you may want to stop at if you are heading west or north of Melbourne on the Western or the Calder highways. We can't assume that it's on the route because it's actually a few kilometres off the route, and that might be significant for planning. And the next simplest thing I thought was, can we just assume that we go in a straight line as the crow flies to and from the projection point on the route? That's also not feasible in this case because obviously you're going to branch off the highway before getting to the charger and branch back onto the highway or merge back on after the charger. So we can't actually accommodate this edge case with our simple model of reality, and it's probably a lot more common than just Shell Colls Express Taylors Lakes. So could we do something a little bit more complicated? Should we, as software engineers, I'm sure we all love the idea of branching and merging. Could we update that simple trip model to include branches and merging back on? This makes it slower because it requires an additional API call to the routing endpoint from Open Route Service. But we also find the issue of Ampol, Foodery, Altona North and Hobsons Bay Civic Centre, that they're both on the same branch. Which of those charges are we going to stop at? How do we model that as part of our simple model of a trip? We could add extra constraints. We could say we only stop at one charger on that branch. And in fact, I went down that dead end a little way before deciding that we're getting too complicated. We've got rules and processing in there just for the sake of a model of reality that doesn't actually fit. So it was time to take... So at this point, the rat's unresolved, but it was time to take the red pill and use another service from Open Route Service, which is Matrix, which gives you pairwise distances between different points, distances and travel times as well. So this has the data that we need to feed into our optimization algorithm, and it's a single API call, very fast. It did require the base constraints that model reality to be updated, so instead of just going from one charger to the next, we actually choose which legs between which cells in that matrix we hop across to get from the start to the origin. So we've updated our model of reality, but it's a much better fit, and we can actually plan trips using real-world data in this case. So RAT's validated, it's on to prototyping. Here I went back to a single trip, and because from Mildura to Malakuta via Melbourne, I just wanted to validate the interactivity. And so here you can see we can slide the range up and down, and we can toggle on and off resilience constraints, and we can see the trip plan updating in real time. It wasn't fancy at this point. I used Streamlit, which is a library and related services that allow you to write pure Python apps, which then can be delivered into the browser in an interactive way. So this was great. The prototype worked really well. I could get a long road trip over 1,000 K with over 50 charges along the way. The interactive planning worked well. I could distribute it to people via Streamlit Community Cloud. But I also found some other things to help with the interactivity. So pre-selecting which charges you're most likely to stop at along the route. As you go through Melbourne, for instance, there are much more than half the charges on the route are in the Melbourne metropolitan area, but you're probably only going to stop at one or two of those max as you go through. So there was another discrete optimization problem to pre-select charges. Variable precision, so we don't always need 1 percentage point of charge. It degrades to 10 percentage points to when the number of charges gets bigger. And I could improve the visualization over those ripples. I thought they were kind of cute at first, but a bar chart worked far better. So that's still online at triplerlight.streamlit.app, but from there, UX validated. The issue in real-world testing would be whether anyone actually wanted to drive this route. We needed, thank you. We needed some additional testing. So that takes us to the MVP. And has anyone got a favourite road trip we should test out? Shout out. To Warrnambool. Melbourne to Warrnambool? Awesome. Oops. There we go. So Melbourne to Warrnambool. Ooh, I'm not spelling correctly, but at least you'll get to see an error message. And so there's the trip from Melbourne to Warrnambool. And we can see charge of pre-selection auto magic in here, which is hidden by default. With the range that we've got, we don't actually need to charge. But if we decrease the range significantly or added more resilience constraints, here we can't actually cross the gap between charges, but we can see different trip plans come up. And something that I also wanted to do every time I travel is learn more about the indigenous owners of the lands that we visit. And so using a service called Native Lands Digital, we're able to find each of the indigenous lands that we visit along our trip. So then we can also launch directions. It's not a direction app, it's a planning app, and so launch directions to complete our trip. So I think I've got to keep moving to ensure we do make good time. Those are the things we saw in the demo. You can visit it there. I may actually test whether my API rate limits and whether my app is resilient to API rate limits at Open Route Service, if everyone tests it today. What I learned was, as you saw, the error message, I had a cactus. I could have fun with the Australian nature of the app. Cactus is obviously Australian slang for something that's broken. On the alternative, things that worked well, I could say she's Apple's mate. But the default flow of the app was that things should just work and it would only call out when things didn't work. So it's been useful to plan trips. Other people have used it, but still not many people use it. And there's a huge range of Python libraries and services that I was able to learn about. No vibe coding required, just really productive programming environment with well-designed abstractions. What's next? So I talked about incremental improvements. So we don't actually have to limit ourselves to 100%. We can extend the model of reality again, because any wall socket could be used to trickle charge an electric vehicle. So there's an option to trickle charge in plans where there's a big gap between charges. Alternatively, we don't have to take the direct route from navigation. We could hop between charges that have enough range for us to reach if we're travelling across more remote areas. And we might also want to consider more detailed factors like elevation. As you go up, an EV turns energy into gravitational potential energy, but you get it back on the down as well. So the other thing we could ask about, what's so bad about stopping when we're charging? So we can actually make the recharge experience better using a similar kind of approach. And so this is Trippler's little sibling, Stoppler. When we stop somewhere in a rural town, we like to get a pie and check out the op shop. So what's the reachable area? Sorry? Big things, yes, big things as well. Great idea. So I would hope that big things would come up in the interesting selection of Flickr photos from the location. But I have to do a little bit of tuning of Flickr's interestingness parameter, but it should definitely prioritise for big things as well as pies and op shops. So yeah, we can think about the trip experience being quite different in an EV and making that a feature rather than a bug. So where might I go from here? It's obviously a hobby project. There's a bunch of things I could do to improve the usability and to solve technical limitations. Like the charger selection is also required so that we have less than 50 points going to Open Route Services matrix solver. There may be ways to explore a scaled deployment model of this. Do I release it open source? There's a bunch of other apps that exist in the EV ecosystem. The services that I used, other trip planners, the charge point operators themselves, and the vehicle manufacturers might all have an interest in having some kind of some part of this experience, or it could indeed be a new standalone planner. I think it also fits into, the one final thing I wanted to say was, it fits into like a bigger picture of how do we most efficiently and most responsively develop electrification infrastructure. And so we have, the way I see it, we have three quite related problems. Route planning is what I tackled with Trippler, but prior to that, I'd actually tackled the network planning problem. So where should we put chargers to enable more trips at the lowest cost? With scarce resources, where do we deploy them to get the best benefit? On another corner of the triangle, we also have fleet planning, like what type of EVs should we have, either as individuals or as organisations that manage logistics. So yeah, maybe watch this space, maybe there's something coming there. And of course, in between, we have integrated planning as well. So networks for routes, routes for fleets, and fleets for networks. And all of these techniques are amenable to operations research, discrete optimisation, digital twins, provided we have access to good data. Or our network resilience improves sufficiently that charger anxiety is no longer a thing, and we don't need trip planning. We just get in the car and drive. So thank you all. Time to stop and recharge. And yeah, you can find more details on my blog, safetydave.net, if you're interested in all the gory details.
Thank you, David. I'm afraid there's no time for questions, but you do get the coveted award.
Thank you, Mike. That's wonderful. Yeah, you can find me afterwards for questions if you like.